What if we could bottle the power of a star and use it to solve Earth's energy crisis? Fusion power promises just that, replicating the reactions that light up the sun right here on our planet. It's the holy grail of clean energy, abundant fuel, zero carbon emissions, and no long-lived radioactive waste. Yet despite decades of research, sustained fusion burn remains elusive. Could we be on the brink of a breakthrough that reshapes civilization? Today we'll explore the science, the engineering, and the global race to build the first practical fusion reactor. From giant tokamaks to tabletop laser systems, fusion takes many forms, but all share a common goal. Along the way, we'll meet the pioneers, the skeptics, and the innovations driving the field forward. By the end, you'll see why fusion captures the imagination of physicists, entrepreneurs, and governments alike. Strap in. Our journey towards star power starts now. Modern society runs on energy, and our demand only grows with every new device and data center. Today's dominant sources, fossil fuels, are finite and drive climate change. Renewables like wind and solar help, but they're intermittent and require massive storage solutions. Fusion, by contrast, taps fuel that is effectively limitless. Isotopes of hydrogen found in seawater. Deuterium and tritium fusion yields about 4 million times more energy per kilogram than coal. A fusion plant could run for millennia on a few tons of fuel. It emits no greenhouse gases and produces only helium as a byproduct. Unlike fission reactors, fusion poses no meltdown risk, and its radioactive waste is measured in decades, not millennia. If harnessed, fusion could power factories, cities, and spacecraft with minimal environmental impact. Fusion research also drives advances in material science and plasma physics. The spin-off technologies, from superconductors to high-powered lasers, benefit other industries. In short, fusion is more than an energy source. It's a catalyst for technological progress. No wonder nations have pledged billions to fusion initiatives. But promises alone won't light the way. We need solutions to formidable scientific challenges. The most mature approach to fusion uses magnetic confinement in donut-shaped devices called tokamaks. Inside a tokamak, hydrogen fuel is heated to 100 million degrees C, forming a plasma of charged particles. Powerful magnetic fields, generated by superconducting coils, trap the plasma away from reactor walls. The international ITER project in southern France is the world's largest tokamak under construction. ITER aims to achieve Q-10, producing 10 times more fusion power than the input. Meanwhile, JET in the UK and EAST in China push the limits of plasma temperature and duration. A key challenge is controlling plasma instabilities that can crash the burn. Physicists use real-time diagnostics and magnetic feedback to suppress those disruptions. Stellarators offer an alternative: twisted magnetic coils that confine plasma without a large central current. Germany's Wendelstein 7X stellarator has demonstrated stable, hours-long plasma discharges. Stellarators avoid some tokamak instabilities, but are far more complex to build. Both approaches require advanced materials to withstand intense neutron bombardment. Research into high-temperature superconductors promises stronger magnets and more compact reactors. The path to a tokamak pilot plant depends on integrating these innovations reliably. ITER's success or setbacks will influence the next decade of fusion development. A second path to fusion uses intense lasers to compress fuel pellets in microseconds. At the US National Ignition Facility, 192 laser beams deliver 2 megajoules into a tiny capsule. The rapid compression raises temperature and density high enough for fusion, but only briefly. Recent experiments at NIF have come within a factor of 2 of ignition. Achieving net energy gain requires even more precise pulse shaping and symmetry. China's Shenlong laser and France's LMJ project pursue similar inertial confinement approaches. Inertial fusion also drives research into advanced target fabrication and high rep rate lasers. Some startups aim to commercialize laser fusion using modular tabletop systems, but challenges remain in scalability, optics durability, and energy recirculation. Success here could yield compact fusion reactors, delivering electricity or driving rockets. The race between magnetic and inertial confinement keeps the field vibrant. Both approaches feed lessons into each other. Advances in one strengthen the other. The fusion roadmap envisions pilot plants in the 2030s and commercial reactors shortly after, realizing the timeline demands breakthroughs in both confinement schemes. Fusion may require parallel routes to find the most practical and economical solution. Beyond standard tokamaks, spherical tokamaks squeeze plasma into a chord apple shape. The UK's MAST upgrade demonstrated high beta plasmas and improved stability. Spherical designs promise smaller reactors and lower magnetic field requirements. American startup Commonwealth Fusion Systems leverages high-temperature superconductors for compact tokamaks. Their Spark device aims for net gain by 2025. In a university partnership, some researchers explore proton-boron fusion, which produces no neutrons and minimal radioactivity. Proton-boron requires much higher temperatures, but yields clean energy. Advanced lasers and particle beams could enable these aneutronic fuels in the future. Blanket designs that capture charged fusion products directly could boost efficiency. As the fuel options diversify, so do reactor concepts. Fusion is far from one size fits all. Building a fusion power plant means solving materials, heat extraction, and safety challenges. Neutrons streaming from fusion must be absorbed by a blanket to breed new tritium fuel. That blanket also transfers heat to drive turbines and generate electricity. Tritium breeding ratios must exceed unity to sustain continuous operation. First wall materials, those facing the plasma, need to endure extreme heat loads. Tungsten, beryllium, and novel composites are under intense study. Remote maintenance systems must swap reactor components in high radiation environments. Advances in robotics and automation are critical for practical fusion power. Meanwhile, supercomputer simulations model plasma behavior and optimize reactor design. Machine learning algorithms are now guiding plasma control systems in real time. Recent breakthroughs include stable burning plasmas at JET and record confinement times at EAST. In November 2023, MIT and MIT PSFC announced sustained high-performance plasma in SPARKIS tests. Those results bring commercial fusion one step closer and invigorate private investment. Still, bridging the gap from experimental devices to grid-connected power stations remains daunting. The engineering team's marathon has only just begun, but each milestone lights the path forward. If the idea of a limitless clean energy future excites you, hit like and subscribe now. Share your fusion-powered visions in the comments. What would you build with star power on Earth? Every like helps this channel amplify the voices driving fusion research worldwide. Ring the bell to never miss our deep dives into the science and people behind the breakthroughs. Join our community of curious minds pondering humanity's greatest technical challenge. Suggest future topics: quantum computing, climate engineering, or next-gen materials. Your engagement fuels the conversation as much as fusion fuels our dreams. Together, we can spark the next generation of innovators and engineers. Thank you for powering up with us. Let's bring fusion energy from science fiction to reality. Imagine a world where power plants mimic the sun, emitting nothing but light and heat. Entire cities could run on reactors no larger than skyscrapers. Developing nations could leapfrog fossil fuels with modular fusion units. Fusion's environmental footprint would pale next to coal mines and oil rigs. In space, fusion rockets could shrink voyages to Mars from years to months. Advanced fusion propulsion may open the solar system to human exploration. Beyond energy, fusion pushes our understanding of matter, energy, and the universe. It tests the limits of what we can engineer and comprehend. Philosophers ask, what does it mean when humans learn to recreate stars? Does fusion mark our mastery of nature or our responsibility to wield power wisely? As fusion research unites physicists, engineers, and policymakers, collaboration becomes essential. The journey to net zero carbon and sustainable civilization may hinge on fusion's success. Every obstacle overcome in fusion deepens our respect for the intricate laws of physics. In that respect, fusion is as much a philosophical quest as a technological one. It reminds us that progress often emerges from the boldest dream. So gaze upward not only at distant stars, but at the science that brings them within reach. Fusion power may one day light our nights and drive our rockets. But first, it demands our ingenuity, perseverance, and collective will. The challenge is immense, yet the reward is epoch-shaping. Humanity now stands at a threshold where we can shape Earth's destiny with star power. Will we rise to the occasion? Or will fusion remain a tantalizing promise? The answer lies in labs, in policy debates, and in the hearts of aspiring scientists. In each experiment, each algorithm, and each engineering design, we write fusion's story. Let that story be one of courage, creativity, and hope. For when we harness the power of the stars, we harness the power of our collective imagination, and that power may prove the brightest light of all. This is fusion's grand pursuit, and it belongs to all of us. Thank you for joining this voyage into star power. Keep questioning, keep innovating, and keep your eyes on the sun, because the future we build could shine as brightly as the stars themselves.